Right now, the Sun is fusing 600 million tons of hydrogen every single second. It has been doing this for 4.6 billion years. And it will keep doing it for another 5 billion. Here on Earth, we have been trying to copy that process since 1952. We have spent over $60 billion. We have the brightest physicists alive working on it. And the joke that every fusion scientist knows is always the same. Fusion is 30 years away. And it always will be. To understand why fusion is worth this obsession, you need to understand what it actually offers. Today's nuclear power plants use fission, splitting heavy atoms like uranium apart. It works. It's low carbon. But it produces radioactive waste that stays dangerous for tens of thousands of years. Fusion is the opposite. Instead of splitting heavy atoms apart, you push light atoms together. The fuel is deuterium and tritium isotopes of hydrogen. Deuterium can be extracted from seawater. Tritium can be bred from lithium. Both are effectively inexhaustible. 1 gram of fusion fuel contains the energy equivalent of 8 tons of coal. No carbon emissions. No long-lived radioactive waste. No risk of a meltdown if anything goes wrong, the plasma simply cools and the reaction stops. If we crack it, energy scarcity ends. Climate change loses its biggest driver. The entire global energy economy changes. That's why $60 billion in 70 years haven't been enough to make people give up. So what actually happens inside a fusion reaction? Take 2 nuclei, deuterium and tritium. Both are positively charged. And like any 2 positive charges, they repel each other violently. This is called the Coulomb barrier. It's the electromagnetic wall that keeps nuclei from getting close enough to fuse. To overcome it, you need to give the particles enough kinetic energy to punch through. And the temperature required to do that is 100 million degrees Celsius. That's 6 times hotter than the core of the Sun. The Sun gets away with lower temperatures because of its sheer gravitational pressure. Billions of tons of mass squeezing the core. We don't have that luxury on Earth. At 100 million degrees, matter changes completely. The electrons are ripped away from their nuclei. You no longer have gas. You have plasma, the 4th state of matter. A swirling, electrically charged soup of bare nuclei and free electrons. And inside that plasma, occasionally, 2 nuclei get close enough. The strong nuclear force, the most powerful force in nature, takes over from electromagnetic repulsion. The nuclei fuse. Helium is created. And a neutron is ejected at enormous speed. Deuterium plus tritium gives you helium-4 plus a neutron, plus 17.6 megaelectronvolts of energy. Every single reaction. Now here's the engineering nightmare nobody warned you about. You need to hold plasma at 100 million degrees. But there is no material on Earth that can touch something that hot. You cannot build a container for it. The moment plasma touches any wall, it cools. The reaction dies. So physicists came up with something that sounds like science fiction. A magnetic bottle. Since plasma is made of charged particles, it responds to magnetic fields. Strong enough magnetic fields can bend, contain, and shape plasma, keeping the superheated fuel floating in midair, never touching the walls. The device that does this is called a Tokamak. A donut-shaped chamber wrapped in superconducting magnetic coils, generating fields powerful enough to bend particles moving at millions of meters per second. The plasma twists and spirals through the donut in a tight ribbon of fire, never touching anything. The first Tokamak was built in the Soviet Union in 1958. The design has been refined for 65 years. And for most of that time, we were putting in more energy to heat and contain the plasma. then we got back out. That ratio, output divided by input, is called Q. For fusion to be useful, you need Q greater than 1. For 70 years, every machine in the world had Q less than 1. The plasma always cost more than it gave. Then came December 5, 2022. The National Ignition Facility in Livermore, California. 192 laser beams, the most powerful laser system ever built, focused simultaneously onto a target the size of a peppercorn. That target contained a tiny capsule of deuterium-tritium fuel. The lasers delivered 2.05 megajoules of energy in a pulse lasting a few billionths of a second. The shockwave compressed the fuel capsule to densities greater than the center of the sun. And the reaction released 3.15 megajoules. Q equals 1.5. For the first time in history, a fusion reaction produced more energy than the laser energy that triggered it. Physicists called it ignition. The room erupted. But, and this is the part that rarely makes the headlines, those 192 lasers required 300 megajoules from the power grid to fire. The system Q, accounting for everything, was about 0.01. We got out 1/100th of what we put in, total. The physics works. The engineering gap is enormous. To power a city, you'd need Q at the system level of at least 10. Probably higher. That gap between the reaction works and it powers your house is the hardest problem fusion has ever faced. So where does this actually leave us? 3 parallel races are happening right now. And for the first time, there's real reason for optimism. Race 1, ITER. The International Thermonuclear Experimental Reactor. A 35-nation collaboration. $22 billion. Being assembled in southern France right now. It's the largest Tokamak ever built. Designed to produce 500 megawatts of fusion power from 50 megawatts of heating input. Q equals 10. ITER won't generate electricity, it's a proof of concept. But Q equals 10, sustained, changes everything. Race 2, private companies with new magnets. Commonwealth Fusion Systems, a spin-out from MIT, developed a new type of high-temperature superconducting magnet that is 40 times more powerful than previous designs. Stronger magnets mean smaller, cheaper tokamaks. Their machine spark is designed to achieve Q greater than 2 in a device the size of a room, rather than a stadium. If it works, their commercial reactor could be on the grid by 2030. Race 3, private investment, full stop. In 2022 alone, private investment in fusion reached $6 billion. More than the entire previous decade combined. The physics is proven. The magnets are better. The money is there. The 30-year joke might finally have an expiry date. Fusion is the most audacious engineering project in human history. We are trying to bottle a star. And for the first time, not in theory, not in press releases, but in actual hardware being built right now. It looks like we might actually do it. Not in 30 years. Maybe in 10. Next up, antimatter. The stuff that should have cancelled out every particle of matter at the Big Bang. Why didn't it? And what would happen if we could make enough of it to use? Subscribe so you don't miss that one. And drop a comment, do you think fusion happens in your lifetime? I want to know.